Lesson 2b, we're going to be looking at the linear time complexity. So, linear time complexity, denoted as ON, describes an algorithm whose performance grows in direct proportion to the size of the input. This means that as the input size increases, the number of operations the algorithm performs also increase. So let's give some examples, some practical examples of the linear time complexity. So I'll just use this PowerPoint slide to show some practical examples of the linear time complexity. Now, example one. Now, before we do that, we need to understand I'll be using a list to showcase a practical example of what linear time complexity is. So we have, let's assume we have a variable called x that holds a list. Let's assume that the list have items of 2, 5, 6, 22. Right? So now let's bring out a problem. So the problem here is to search for a target number in the list. Right? So now this is the problem. The problem is to search for a target number on the list. So let's assume that the target number, let's assume we have a variable called the target number, and the target number is 22, and we want to write an algorithm to search for 22 in the list here. Remember that x is a variable that holds this list, and the problem is to search for a target number on the list, which is 22, right? So now doing this, we all know that writing an algorithm to find 22, the computer doesn't, by default, the computer doesn't have any instruction to do that, and the constant time complexity cannot actually do that. So what need to do here, we need to look through this list here in order to find where 22 is located in this place here, in order to find 22 here. So now what do we do? Now there are two things to do. Now we can decide to use the conditional if statement. But the disadvantage with the conditional if statement is if there are n numbers here, right? So that's why that means you need to have an n conditional ifs. So the best way to write the algorithm is to look through this list and then use a conditional if to find them, to compare this target number one after the other with the indexes in this list. So how do we do that? Now, the first thing is to look through, let's assume we want to look through, so for I down to the length of x. So now let's explain what this does. Let's explain this step. So let's assume for I is equal to 0. So it means that in the iteration, I is starting. Remember the list here, we have this 2 is located in index 0, 5 is located in index 1, 6 is located in index 2, and 22 is located in index 3, right? So now we want to write an algorithm to find 22, which this is the target, and the target is 22. So now we'll start our iteration by having a variable called I. This variable, it not necessarily must be I, it can be any alphabet, right? So the variable is starting the iteration from the 0 down to the length of x. And the length of x is, we count the total number of items in this x. Remember the x holds this list, which is 1, 2, 3, 4. So 4. It means that when you pass this instruction to the computer will iterate 4 times starting from 0, which is like this. So for I is this. So you're telling the computer to start I equal to 0, then it will go 4 times, which is I equal to 0, I is equal to 1, I equal to 2, and I equal to 3. which is 1, 2, 3, 4. So this is the 4 times the computer will iterate, right? That is the instruction, that's the first instruction you pass to the computer. So what if we say length of x minus 1? So it means that you are telling the computer to say length of x is 1, 2, 3, 4, right? So it will be 4 minus 1, which means you're telling the computer to iterate 3 times. 4 minus 1 is 3. So starting from I equal to 0, which means it will be I equal to 0, I equal to 1, and I equal to 2. So the computer will skip this. So what if I tell the computer to start I equal to 1 and then the length of x minus 2? So what happens? It means that the computer is starting I equal to 1, right? So let's assume I by default, remember by default the index starts from 0, right? I equal to 0, I equal to 1, I equal to 2, right? If you count the total number of items you have here is 1, 2, 3, 4, right? So it's 1, 2, 3, 4, I equal to 3, right? So now, looking at this instruction, you're telling the computer to start from I equal to 1, which means the, then I equal to, is starting from I equal to 1, and then the length of x is 4, right? It's 4, 1, 2, 3, 4, minus 2, which is 2 times, right? So now, the first thing is this 2 times is 1, 2. So the computer skips this, right? It skips this. So the computer is only running this I equal to 3, I equal to 1. But now in this first phase here, you're telling the computer starts from I equal to 1, which means the computer will only run one iteration. So these are some basic instruction. So the computer will only run this I equal to 1. That's all, just one iteration. That is what you tell the computer to do here, right? So what if you put, right? So that is how to read, that is how to pass instructions to computer, and this is what the computer will perform. So let's get to our problem. So our problem here is to search for a target number on the list, and the target number is equal to 22. So to search for that, I will say, okay, computer should start from I equal to 0 down to length of x, which means it starts from this I equal to 1, I equal to 2, and I equal to 3, right? So it's 1, 2, 3, 4, which means saturating 4 times. So now the next line of code here, the next line of the pseudocode here is to use the conditional if statement to compare them. So if, right? So now we want to like fetch the value from the index. We want to fetch the value from the index. So to fetch value from the index, I can say the x of the I, right? If the xi, so I'm fetching this value now from the index. If the si is equal to this target number, right? So I may return, no, let me print or output. Let me use the word output I. So output I, it means that you are outputting the index where 22 is located. But if I say I output x I, it means that I'm outputting the number. But the problem here is search for a target number in the list and return the index where the number is located. And return the index where the target number is located. So now we have the for I equals to this. Now if this is equal to this, then return the I. So I is returning the index and the other one is returning the value. So you can see I've written a simple algorithm to search for 22 in this list and then return the index where 22 is found, right? Then I can try to put x output 0. else outputs I, or else output should I put not found? Okay, let me put not found. Else outputs not found, right? So now let me remove this. So we have understood the first step, right? So the first step is starts from the I equal to 0 and then it's looping 4 times, right? So now this second step is, remember this, if this one here, this x of I is fetching the value, it means that in the first iteration, it means that what it means is when I is equal to 0, so what happens in this line? So when I is equal to 0 in the first iteration, so the line will give you, it will fetch out the value in where in index 0, which is 2. It means if 2 is equal to 22, which is a target number, so output I. But in this case, this one is what? False. So it will output not found. Right. So now in the second phase, when I is equal to 1, right? So it means that it will fetch the value in index 1, which is 5, right? So it's where it will now be if 5 is equal to 22, so it's not found. So it goes again when I becomes what? 2, right? So it fetch out the value in index 012, right? In index 2, which is 6. So this becomes what? 6 equal 22 not found. So when I, the last one is when I becomes 3, it will go again, it fetch out the value which is 22. Now equal this, which is found. You can see. So now it means that it will now return, this output will now return index 3, right? So the output will now return index 3. So that is how it works, right? This is a simple algorithm to search for a target number in a list. Now let's do another problem. Let's do another problem. So now let's try to find, let's try to write an algorithm to search for search for a maximum number in the list, right? So you can see in the previous problem, you can see what it does, right? It compares them linearly, one after the other. So remember that when we are doing the iterations, we're saying the length of x, which is 1, 2, 3, 4. You can see we have 4 iterations. So what if there are another number here, like 55? You can see that this is the n. So n is equal to 1, 2, 3, 4, 5, right? N is equal to 5. Here, remember in the previous one, we have n equal to 4. You can see that the size of n grows. So that's why the size of n grows and we are looping it through linearly, right? So that's why we say that this operates on the linear time complexity of O(n), right? We're using a single loop and the size of n grows, right? So that's why we're operating on a single loop, which is O(n) squared. Now, what we just did was in the worst case scenario because 22 was in the last index. So in the best case scenario, we can have in the best case scenario, there may be a situation whereby the target number we're trying to look for in the best case scenario, there may be that the target number we're trying to look for here is 2. Let's say the target number is 2, right? So 2 is in the first index here. So when we write an algorithm to find 2, right? So definitely it will, this is in the best case scenario, but that doesn't mean, so if you're writing an algorithm to loop through this list of item and then find a particular number here, the best case scenario is to operate on O(n), right? On a linear time because it's looping through and then searching them one after the other. But there's what we call optimize and non-optimize. So we can decide to optimize the code whereby when we find the target number, it should break. So I will do that later when we look at this problem, right? When we look at this problem, right? So in this place, in searching for a maximum number, the worst case scenario is ON, the best case scenario is ON, and the average case scenario is ON because everything has to do with the loop. As the size increases, we are still like comparing each one after the other. So in this problem here, we'll look at optimize and unoptimized algorithm here. So let's do a second one. So write an algorithm to search for a maximum number in the list. Right? So now what do we do? Assuming that we have this number, right? So the first thing we do is remember that you're passing the instruction to the computer to find the maximum number in the list, and the computer doesn't know the maximum number here. But you as a human, right, and you as a developer, you need to write an algorithm in order for the computer to understand the n number here and then find the maximum number, right? So what happens? What do we do? The first thing we do is to write a for loop, which is for I. We start the I equal to 0, then down to the length of x, the length of this x. Now there's something we need to do here. Yeah. So here, let's assume right that the first number is a maximum number. Now let's assume before we write that going, let's just do some um check. Let me remove this. So in this problem here, okay, so let's assume that the maximum number is the first number, right? So when the maximum number becomes the first number, then we'll compare all these with the first number. So any number that is larger, that is any number from here that is larger than the first number, right? Then save the large number to the max number. So what do we do? What I will do here is what I will do here is I will have a max number variable like this that will hold the first number, right? So what I did here is I have a max number. Let me put this sign here. So, right? So this sign means the x0, it means you have saving this to value 2 to the mass number. So this mass number is holding 2 at first instance, right? That is what I did here. It's holding 2. So now for I in the range of, so instead of me starting from I in the range of 0 again, where we have already fetched in this value 2 down to this mass number here, I can decide to start from 1, right? I can decide to start from 1, then down to the length of x, which means that for it, okay, let's start from 0. Let me just explain something from this, which means that I equal to 0, right? I equal to 1, I equal to 2, I equal to 3, I equal to 4, right? So because we have 1, 2, 3, 4, remember the length. We have 1, 2, 3, 1, 2, 3, 4. Sorry, there's no I equal to 4. So it's 4 iterations, 1, 2, 3, 4. So remember that when I equal to 0, right? When I equal to 0, the x of I here is equal to, we give you what? Equal to, right? The x of I is 2. So when I equal 1, then x I here is 5, right? So when I equal 2, x I here is what? Is 6, right? So here, when I equal 3, x I here is 22. Okay, now this is how it works. It iterates through, and this is when I is 0, so this is the value 2. When I is 1, this is the value 5. When I is 2, this is value 6, and when I is 3, this is value 22. Right, so we are trying to find the maximum number. But now, in the first instance, we've already assigned when I equals 0 here, the x0, right? X0, we have assigned to this mass number, which means the mass number holds 2. So the computer assumed that the mass number is 2 at first instance as first iteration. So now when coming back for I in this, so instead of starting from 0, which is already 0 is already 2, we can start from 1. Right? So now we'll use our conditional if. So if xi, right? If xi is greater than the mouse number, so what happens? So what happens? It means that the mouse number should collect the xi number. Should, right? It means that the mouse number should collect the si number. Right? So that's what happens here. So it means that, okay, now let's do it. So in this iteration now, for I equal to this, it means that we have iteration 1, iteration 2, 3, and 4. And this iteration, when I equal to 0 is out from this iteration here, based on this our algorithm here. So we are left with I equal to 1, I equal to 2, and I equal to 3. So in this phase there, if I equal to 1, which is 5, right? So what happens? So if 5, it means that if 5 at first iteration, if 5 is greater than 2, so what happens here? If 5 is greater than 2, then store 5 in as the new mouse number. So the new mouse number here will become what? The new mouse number here will become, let me write it here. So the new mouse number here will become what? 5. So in the second one again, remember the mouse number is 5, right? Remember it's 5 now. So in second one again, when in the second iteration, coming again, I when I equal to 2, so I of x becomes what? 6. So if 6 is greater than 5, what happens? If 6 is greater than 5, what happens? It means that we should store 6 as the new mass number. Then in third iteration, right? In third iteration, which is 22, right? So it means that if 22 is greater than what? 6, it means that store 22 as a mass number. And then it will stop. So in this algorithm, so let me remove this. So this is a simple algorithm to find the mass number. Now, this is the worst case scenario because the number we're trying to find is in the last index. So in the average case, the number we're trying to find may be in the middle item in the list. Then the best case, the number we're trying to find may be in the first number in the list, like this, 22, and this becomes what, 2, right? So this is the best case scenario. So what happens? Should we would say that if we are writing this algorithm, like this is the algorithm, right? This is the algorithm. So even if the number were the largest number is 22, right? In the best case scenario, in the best case scenario, you won't say is operates on a constant time complexity because these have defeat that constant time complexity because you are comparing them one after the other by looping through and getting total number of iterations here. So this does not stand for constant time complexity. So in the best case scenario, whether the largest number is in the first place, then or in the second on the second place, this works on the big O of n, which is a linear time. So in the average case is still linear time. Then the worst case is still linear time. But however, you can optimize this algorithm. You can optimize this algorithm, right? So in order to optimize this algorithm very well, so what you need to do here is now once I find my answer, it will break. But in this position, there is no way you can optimize the algorithm because the computer doesn't know that this first one is actually the largest. So the computer must definitely compare this down to the last. So in this part here, right? In this part here, this is a perfect algorithm to run this because the computer will compare each of these items in order to find the largest number. So another problem of writing this to find the minimum number. So what if I want to find the minimum number? So what if I want to find the minimum number in the list? So all I just need to do is to change the sign here. So less than, right? So it's the same pattern, the same explanation. and the worst case, best case, and average case all operate in the linear time complexity, which is big O, which is big O of n, right? So there are other examples of linear time complexity, but these are just basic examples of linear time complexity. I hope you understand this, right? So in the next tutorial, we're going to be explaining the quadratic time complexity and the exponential time complexity so that you can understand what this means. So these are the three basic examples of linear time complexity, right? So when you are given a problem to solve, all you just need to do is to understand the problem and then decide on how to write the algorithm, and then you can be able to detect the time complexity that algorithm falls into, right? It's very, very simple. So thank you and God bless you.